In this second example, the directions tell us use the limit process to find the area of the region between the graph of the function and the y-axis over the given interval. Notice they're telling us how to do it and finding the area, not approximating the area, finding it, the exact area over the given interval. Notice that this is a function of y, therefore this interval is from the y coordinate 1 to the y coordinate 3, but this is still our interval on a to b. So if it's saying find the area of the region, that's the exact area. We're going to be using our limit process. Limit as the number of rectangles goes to infinity. The sum from the first rectangle to the nth rectangle of the areas, the width times the height. So remember, we need to work from the inside out, find the width and find the height first so that we can plug it in to the summation. So our width first, our delta x, that's our b minus a over n. We can use these values and just plug them in, 3 minus 1 over n, 2 over n. We can also find the f of c sub I by first finding the c sub I and plugging it into the f, and all of this can be done without a picture. However, it does make more sense with a picture. So let's practice graphing this function of y. You can think of this as x equals y squared plus 1, and we are looking from the y value 1 to the y value 3. This is a y to another y, the first y to the second y. So we want to be able to spread that out a little bit. So let's count 1, 2, 3 this way. And thinking about if we plug the y value 1 in here, 1 squared plus 1 is 2. However, plug 3 in, the upper limit of our interval in, 3 squared plus 1 is 10. So we need to go all the way up to 10. So we want to count differently on this axis. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and that'll fit in there nicely. So plugging the y value 1 in, we get the x value 2. So plug the y value 1, we get the x value 2. Plug the y value of the upper limit in, 3 squared plus 1, that's 10, so the x value 10. Let's also plug in the 2 into the y, 4 plus 1, that's 5. So the 2 goes with 1, 2, 3, 4, 5, like that. And then we can also think of this as a parabola that's opening to the right instead of up because it's y squared, and it's been shifted up 1 away from the origin, and by up, we have to mean, in this case, in the x direction, 1 unit. So the vertex would be here, and then it would be half of the parabola. We'd see the other half coming this way if we had room to graph all of it. And then we only want on this interval 1 to 3, so from 1 to 3, and remember that they said to find the area between the graph of the function and the y-axis. So here's the y-axis, and here's the graph of the function. So we want this area in there. That's the area that we're finding exactly. It also is helpful to have a picture because then once we get an answer, we can tell if it's a logical answer, if our numbers make sense. So let's continue and we'll check that at the end. So remember our c sub I is the starting value plus I amounts of delta x away from the starting value. So we're given the a as 1, so plug in 1 plus I, 2 over n is our delta x. We're going to need to use that. So now that we have c sub I, we're going to plug it into f of x to find f of c sub I, or the height. Now keep in mind that we're treating y as x to make it more familiar, but in actuality this is f of y. So we're plugging in the y into f of y. Remember that delta x is what we're used to saying, but in this case, because it's f of y, this is the change in y. This is delta y, because we're subtracting the y values on the interval 1 to 3. 3 minus 1, the y values. So anyway, let's go ahead and plug this in to our function. Since this is the y value, this helps us get our height. So see that the y is squared. So instead of y, I'm going to plug in 1 plus I times 2 over n. That got squared, so this gets squared, and then I have to add 1. Remember that this means that I'm multiplying this to itself. And then don't forget the plus 1. So when we FOIL this, 1 times 1, 1 times 2i over n, and another of those makes I times 4 over n, plus I times I is I squared, 2 times 2 is 4, n times n is n squared, and then of course we have plus 1 from the end here. So let's remember that we're combining those like terms when we go to plug it into our limit expression. So this area will be the limit as n approaches infinity of the sum from I equals 1 to n. Instead of delta y, we'll put what delta y equals, 2 over n. And instead of f of c sub I, we'll put what that equals, which is 1 plus 1, 2 plus I times 4 over n plus I squared times 4 over n squared. Now we'll simplify the summation expression so that we can use our shortcut rules. First thing we'll do is notice that I is the only thing varying here, so anything that's not I is not a variable and can be pulled out of the sum, such as this 2 over n, that's considered a constant, and it's multiplied, and we can pull out constant multiples according to our sum rules. So let's rewrite this limit expression. The limit as n approaches infinity, 2 over n times the sum from I equals 1 to n of 2 plus, you know what? Well, nah, let's take our time. One step at a time. Now we can break this up and take the sum of each of those. So let's go ahead and do that. 2 over n times the sum of 2 plus the sum of I times 4 over n plus the sum of I squared times 4 over n squared. Each of these, of course, going from 1 to n. Within each of those now, we have a constant multiple. Remember, I is the variable because counting I equals 1 counts up to n is the constant up to n rectangles. So we're pulling out the constant multiple from each of those summations. So now the limit as n approaches infinity of 2 over n times the sum from I equals 1 to n of 2 plus, bring out the 4 over n, sum from I equals 1 to n of I plus, bring out the 4 over n squared times the sum from I equals 1 to n of I squared. Now we can use our formulas to find the sum of 2, which is just 2n, going from 1 to n, the sum of I, n times n plus 1 over 2, and then the sum of I squared, n times n plus 1 times 2n plus 1 over 6. Let's write down everything else that's around that, such as the 4 over n squared added to the 4 over n coefficient and the 2 over n multiplied to all of those, and see what simplifying we can do next. Like n divides out with n, 2 goes into 4 twice, 1n from here, taking 1 away from here, 4/6 to make 2/3. This becomes the limit as n goes to infinity of 2 over n times 2n plus 2 times quantity n plus 1 plus 2 times quantity n plus 1, quantity 2n plus 1 over 3n. And now we can distribute this 2 over n to those three expressions. Now it looks like we're running out of room, but we're almost done. 2 over n times 2n, these n's cancel out to leave us with 4, plus 2 times 2 for 4, n plus 1 with an n in the denominator, plus 2 times 2, again for 4, n plus 1, 2n plus 1. And then the denominator, this n gets multiplied to that 3n for 3n squared. And now let's take the limit. So the limit of 4 is just 4 plus, because this is n going to infinity and these are equal degree, we'll take our leading coefficients, which is 4 over 1, or 4, plus, these will also be equal degree because when we multiply by 4 and then multiply by 2n in the FOILing process, that makes 8n squared. N squared, n squared, use the leading coefficients, 8 over 3, so 8/3. 4 plus 4 is 8. 8 plus 8/3 means 32/3, or 10 and 2/3. And if we compare it to what this area is approximately, maybe look at it like a large rectangle where this is about 1, 2, 3, 4, 5, 6, 7, 8, 9 blocks long, and this is 1, 2 blocks wide, 9 times 2 being 18, but our actual area is way less than 18. 10 and 2/3 really does make sense. I know this process sounds like a lot of work and possibly a little confusing right now, but keep practicing, maybe watch it again, and you'll get it. See you in class.